So good morning everyone. Now this is our third day and we are going to start the first session. So for this session we have with us Dr. Rabindranath Adda. So before going to discuss about the session and brief the speaker, I would like to request our colleague Dr. Das to please welcome the today's speaker to the bouquet and through, please. So once again I welcome today's speaker Dr. Rabindranath Adda. Dr. Rabindranath received his BTech from Andhra University in Electrical Engineering, MTech and PhD in Electrical Engineering from Indian Institute of Technology, Kanpur, and presently he is working as the Assistant Professor in the Department of Electrical and Electronics Engineering, IIT Guwahati. So Dr. Adda till now published more than 40 research papers in various journals and conferences. He is guiding PhD students, so he is very active in this field of the, you can say, power quality and renewable energy field. His research interest includes the distributed generation, PWM control of inverters, power quality, digital control of power electronics. So with this brief intro, I would like to request Professor Adda to please start the session. Thank you very much.
So, thank you, Professor again. So, I also thank you and the organizers for inviting me to this event so that I get an opportunity to interact with all of you. So basically, before starting my actual presentation, I want to give a brief introduction about the IEEE department and then the IEEE BELS chapter at Guwahati and what are the benefits of IEEE. Because through IEEE and other platforms only we get all the knowledge and help to do more research. So let me just talk about the department. So basically the department of IEEE is established in the year 1995. Like the IIT Guwahati is also started in 1995 and our department is also started in 1995. So during that time very less number of faculty used to be there. But currently we have around 51 faculty members and we have total 20 technical staff and 3 office staff. So total 23 staff members are there. So we have faculty members working in almost all major areas of electrical engineering. Like we have power engineering, in which we have power systems, power electronics, high voltage engineering, electrical machines, electric vehicles and all. And we also have other specializations like control and automation, signal processing, communications, microelectronics and VLSI, and RF and photonics, and of course nano electronics and all. So basically we work from DC to megahertz. So we say that electrical engineers, so DC means DC power supplies, and then 50 Hz which is power engineering, and then we have some 10 kHz, 20 kHz switching frequency which is like power electronics. Then you go to megahertz, that is microwave frequency. So we work from DC to megahertz. So then the department currently offers 2 BTech programs, one in ECE and another in EEE. So ECE we have around a strength of 120 and then EEE we have around 65. Then we also have 6 MTech programs in various specializations. Like in all these specializations, we have one MTech program, and we have a PhD program. So currently we have around 700 BTech students. So per year the intake is around 180. So for 4 years we have around 700, and then 200 MTech students and 200 PhD students working in different areas of electrical engineering. So this is a brief introduction about the department, and basically if you know any BTech students etc., we have a summer internship program now. The department offers summer internship for people who completed BTech third year. So the form is available in the department website. So you please visit, and if somebody is there, you can please refer. And also, if you want to work with any faculty through your supervisor, you can just approach us, and then if there is any possibility, we can work together. Okay. Then the second part is IEEE PELS chapter. So basically, through IEEE only we just get so much knowledge about what is power engineering and what are the researches going on in the field. So we just started this IEEE Power Electronic Society recently in Guwahati, and it is inaugurated by Professor Sanjeev Kumar Panda, who is IEEE PELS Asia Pacific Region Coordinator. And currently we are the office bearers, that is Dr. Chandan Kumar is the chair, and myself I am the secretary, and then Dr. Ankush Bagh is the treasurer. Okay, so why this IEEE PELS chapter is important? Why do we start? So basically there are so many benefits which we are going to explain. So for example, we can have different activities under PELS chapter. Okay, so here we had a distinguished lecture by Professor Sanjeev Kumar Panda on his research area. So he has delivered a lecture, and similarly we have also organized Professor Pradeep Barwa's lecture. Okay, so if you want the local arrangements, expenditure, etc., we get from PELS, and through PELS chapter we can also contact them and invite them to deliver lectures here, so that we get more awareness about what is happening in the field. Similarly, there are other advantages also. So if you see the IEEE PELS, basically it is founded in 1987 as a Power Electronics Council. It was operating initially, then it is changed to IEEE Power Electronics Society, and currently we have around 10,000 members in the world. Okay, and we have both student members and graduate members. And what are the benefits of IEEE PELS membership? So if you want to become a PELS member, first you should become IEEE member, then you take IEEE PELS membership. And for students it is very less, I think it is around $4 to $5 only, the IEEE PELS membership. So you have subscription, that is subscription to the different magazines and different journals. Okay, so even if your institute doesn't subscribe to these journals, you can access through your IEEE account if you are a PELS member. Okay. Similarly, we also have registration discounts in conferences, symposiums, and workshops. Like if you are attending any workshop or a conference which is technically co-sponsored by IEEE PELS, you will get some 10% or 20% discount on the registration fee. Okay, already we have very less support from the institutes to attend the conferences. So if you just become this PELS member by paying $5, that is around let us say 400 rupees also, so you will get the same in return if you are attending any conference. Also, we have a multimedia online library where we have all the webinars and distinguished lectures, tutorials. So much material is available in the multimedia online library, which is accessible to all PELS members. And we will get an opportunity for networking. Okay, for example, we have around 208 chapters worldwide, and there are so many members. Okay, there are so many student branches also. And if you are a PELS member, you can just attend the networking events organized at major conferences like APEC, DCCE, and Compel, PEDG, etc. And members can also participate in technical committees, conference committees, and the chapters. And only, especially for women, there are some events like women in engineering events or social gatherings. So for women, because we have to encourage a number of women in this field. So we have women in engineering events separately, and we also have mentorship events. So these are some of the benefits of IEEE PELS membership. Then we also have a distinguished lecturer program. So if you have IEEE PELS chapter at your location, you can invite any of these people to deliver a lecture at your location. Okay, so we need to take care of only their local expenditure. These are all foreign professors, so we need to take only their local expenditure from Delhi or Bombay to your place. But the international travel will be taken care by IEEE. So that is possible only if you have a IEEE PELS chapter at your location. Okay. So similarly, we also have many education or student activities. For example, IEEE Future Energy Challenge, where we hold a competition and then IEEE will select some people. And we also have student travel grants. If you are a PELS member, if you are attending any conference, you have opportunity to get student travel grant. Similarly, there is something called IEEE PELS PhD thesis talk award. So if you have completed PhD freshly and then if you want to participate in this, we just have to send a video of up to 3 minutes. Then they will just filter out based on certain parameters and you may be considered for this award. So these are the education and student activities. So thank you very much. Basically, these are the benefits of IEEE PELS membership. And what I suggest is, at least if you are student members, 6 student members, you can start a IEEE student branch. Okay, IEEE PELS student chapter. So for that only 6 student members are required. So at least you can initiate that student branch. And if you have many members like faculty members who are IEEE members, not the student members, you can also think about the IEEE PELS chapter. Okay, so if you require any other further assistance, you can contact any of us like Dr. Chandan Kumar or myself. These are my our email IDs. So you can please contact us if you need any help to start your IEEE student branch. Okay, so that is about the IEEE PELS and IIT Guwahati. So now let me go to the actual lecture. Okay. So I think how do we exit this?
Sir, escape. Keyboard. Escape.
Yeah, keyboard. Yeah, I could not locate that. Okay, so now we will go to the actual part of the lecture. So basically I am going to discuss about power quality, what are the common problems of power quality, and then what is the importance of power quality and how do we analyze some of the problems and what are the possible solutions. Okay, I am not going to detail any solutions. In the next part, second part, we have a research paper presentation in which I am going to explain one of the solutions very detailedly. Okay, so now this is the overview of the presentation. So I will start with introduction to power quality and the classification, like different power quality problems, and then how some case studies also. Like I will show you some example systems where power quality can be seen, power quality problems can be seen, and how do we characterize power quality? What is the financial impact of power quality? Because financial impact is very important before which we can do any analysis. Now, analysis of unbalance and harmonics and solutions for power quality issues. So these are the topics that I am going to cover in the first part of my presentation. So power quality, we have a definition of power quality. This is the formal definition given by IEEE. But in generally, if you want to talk about power quality, it means supplying electricity to customers with minimum distortion and interruption. Okay, so we should not have any distortion in the waveform, and we should not have any interruption in the power supply. If we can ensure that, then we can say power quality is good. Now, the power quality problems can be quantified in terms of voltage, current, frequency. Okay, so voltage has a nominal value, it is 230 volts RMS, and current should be sinusoidal or as required by the load, and then frequency should be within the tolerance. Okay, then we can say that the power quality is good. And also, if we don't maintain these values, there will be more operation in the customer's equipment. That is why you want to maintain these 3 parameters. Now, we can see the ideal voltage waveform here. This is a single phase sinusoidal waveform and 3-phase sinusoidal waveform. So, if the power quality is good, we should get a voltage waveform like this. But what will happen is, in case of non-ideal case, we can have different problems in the waveform. So, we can have a voltage sag where there is a decrease in the peak value for 2-3 cycles. Then we can have a voltage swell. Swell means increase in the peak value for a few cycles. And short interruption, that means there is no power for 2-3 cycles. Then oscillatory transients, that is peak value is changing continuously, and there is also a exponential damping kind of thing for the peak value. Then this is the harmonic distortion. So along with fundamental, you have a fifth harmonic, seventh harmonic component, and we can have an unbalance in case of three-phase waveform. So peak values are not same, and we can also have a case where both unbalance and distortion is present. Okay, then we can have notching and flickering. So there are so many other issues. We can just see all other issues. So what is the impact of this power quality? So basically, if you have power quality problems, there is mal-operation of the customer's equipment. And also, for example, if you have a microprocessor or any other IC, like digital control ICs, they have very sensitive voltage. Like the supply voltage is, for example, 3.3 volts. The tolerance is very less. It is not even 1%. Less than 1% tolerance will be there. If voltage deviates beyond that point, the microprocessor will damage. Okay, let us say you have to give 3.3 volts supply to the IC. If the voltage becomes 3.5 volts, then the microprocessor will damage. If the microprocessor will damage, your entire equipment will come to standstill. Okay, so that is one important problem. Then another important problem is the production loss in processing plants such as semiconductors, food processing, or any other. For example, due to some voltage sag or voltage swell or harmonics, one of the machine is not operating as per the requirement. Then you have to stop the production for some time, and if you stop the production for 1 hour also, there is huge loss in the industry. And also sometimes if you have sustained power quality problem, the machine may damage. If the machine damages, getting it repaired is not so easy. For example, if you are operating a machine in Agartala, the experts will come from foreign. Okay, we don't have many experts to repair special industrial machines. So somebody will come from foreign to Agartala and repair it. The entire process will take at least 6 to 7 months. So 6 to 7 months you don't have any production, and there is no employment for that particular industry. So we have to address it before the machine damages. So we also have problem of mal-operation of production systems. So sometimes due to voltage sag and swell or harmonics, the relays may operate thinking that there is some issue in the voltage or current, and there may be power interruption. So these are the impacts of poor power quality, and we will also see financial impact soon. And we can categorize the power quality problems like this. There are so many categories. For example, transients, short duration voltage sags, and then long duration voltage variations. So long duration means it is greater than 1 minute, short duration is less than 1 minute. And then we also have voltage unbalance, waveform distortions, voltage fluctuations, power frequency variations, and noise. So most of these problems we saw waveforms in our previous slides. So we will see what is the source of these power quality issues. Why are you having these power quality issues? Basically, we have 3 different sources. We can classify them. One is from the utility side, another is internal sources, and then power electronics related operators. So now utility side, basically these are the utility side issues like lightning strike or power factor correction equipment, faults, and the switching of any other equipment. For example, there is a lightning strike at a source side, there will be impact on the bus voltages at the customer side. So this is categorized as a utility problem. Okay, although it is nature problem, we just categorize as a utility problem. Then we have internal sources like we have some individual loads like induction motor loads or arc welding or medical equipment which are actually creating harmonics in the system. And we also have power electronics based operators. So all these operators will pollute the voltage and they will inject harmonics. So these are the major sources of the power quality issues. Now we will have some case studies. We will see some examples in a simulation based system. What are these transients and what is the harmonics and how this unbalance will happen. So for example, if you consider an impulsive transient or oscillatory transient, there is a difference between the two. Impulsive transient means it is unipolar in nature. It can be either positive or negative. Oscillatory transient is bipolar in nature, and there will be some 2-3 sinusoidal terms like with different frequencies. So impulsive transients are caused by lightning strikes, and oscillatory transients are caused by transformer or induction motor energization. So we will consider a system here, radial 2-bus distribution system. So this is our source, and we have 2 feeders and 2 load buses. So load is connected at bus 1 and bus 2. Let us consider first case where we have a lightning strike or some kind of impulse at the source, and what is the impact in bus 1 voltage and bus 2 voltage. That is one case study. Second case study is we will connect a capacitor here at bus 1 and see what is the impact. Okay, so in the first case, this is voltage impulse at the source, which is around 10 per unit, and you can see the bus 1 voltage is suddenly increasing to 7 per unit, and bus 2 voltage is increasing to 5 per unit. Okay, so from this what we can see, the impact of the lightning strike or voltage impulse depends on the location of the load. If it is very near to the load, very near to the voltage impulse, then the transient is more. If it is far, then the transient will be less. So, but of course, there is a sudden increase in the voltage because of which some equipment may malfunction. Now, let us say at load 1, I have connected a capacitor, okay, and I will do the same step. So, there is a capacitor at bus 1. So, instead of sudden increase, there is a oscillatory transient here. You can see there is a same impulse at the source, but bus 1 voltage is oscillating and it is settling within 1 cycle. Similarly, bus 2 voltage also has oscillations. If you consider the peak value here, previously the peak value is increasing to 7 per unit and this is going to 5 per unit. But here the peak value is less, it is 4 per unit here and it is around 3 per unit. The peak value of the impulse will decrease, but there is some sustained oscillations for 1 or 2 cycles. So this is basically showing that the response to transients depends on the nature of the load. Previously we don't have a capacitor, now we have a capacitive load, and also the location of the impulse. Okay, so this is one case study where we can see oscillatory transients and impulsive transients. And we can also see another case study where we consider voltage sag or voltage swell. Okay, voltage sag means increasing the peak value for few cycles. Voltage swell is voltage sag is decreasing the voltage and voltage swell is increasing the voltage. So let us consider a 3-bus distribution system here, and this is a voltage source and there is a delta star transformer. So what happens is there is a single line to ground fault at bus 1 and there will be some voltage sag and swell in the system because of this single line to ground fault. So we can see the waveforms here. This is phase A voltage, this is phase B voltage and this is phase C voltage. Okay, so there is a single line to ground fault in phase A at bus 2. So because of this we have a decrease in the voltage peak value in phase A and increase in the voltage peak value in phase B and C. So same fault has different effect in phase A and different effect in B and C. So this is showing what is the source of the voltage sag and swell. Okay. So once the fault is clear after 3 cycles, the voltage becomes nominal value. Now we will also see one more case study when we talk about harmonics. So this is the 3-phase system where we connect an unbalanced and distorted load, and the load voltages are VTA, VTP and VTC, and load currents are ILA, ILB and ILs. This is the unbalanced and distorted. Now the load is drawing unbalanced and distorted load, distorted current. The source is balanced and it is also sinusoidal. But what happens is, since ILA is distorted, what is the voltage VTA here? VTA is VSA minus ISA times the feeder impedance. Okay, ISA has harmonics. Because of these harmonics, the VTA, the voltage at the load, will also be polluted. Okay, so we will see the simulation here. For example, these are the currents drawn by the load. You can see these are unbalanced and they also have harmonics. So the figure at the bottom shows the voltage at the load terminal. So the black color one is voltage at the load terminal. This is also distorted. Okay, so basically our source current has no problem. The source voltage has no problem. It is ideal. But because of this unbalanced and distorted load, the load voltages are distorted. Now this is some customer. Some customer 1 has connected this load. Let us say I have a customer having only linear load. Only some RL load is there. If I want to connect at the same bus, I will also get the distorted supply. So I am not polluting the load, I am connecting a linear load only. But because of some other customer, my load is also affected. Okay, so this is the case study of harmonics. Now, how do we characterize this power quality problems? Like before we solve power quality problems or find out the solutions, we have to characterize them. So, this table shows characterization of different power quality problems. For example, if you have a transient will be characterized in terms of peak magnitude, rise time and duration of the transient. Okay, so if peak magnitude is more, transient is more serious. If peak magnitude is less, transient is not that much serious. Similarly, rise time. So if rise time is high, then it is more serious. Duration of the transient also matters. Similarly, if you have a short duration voltage variation, it will be characterized from the magnitude and duration of the voltage side. And we have voltage imbalance. Voltage imbalance is characterized by symmetrical components, positive sequence, negative sequence and zero sequence components. And waveform distortion is characterized by the total harmonic distortion and the harmonic spectrum, like what are the types of harmonics in the waveform. And voltage flicker is characterized by frequency of occurrence and modulating frequency. So that is how we characterize the power quality problems. And based on the characterization, there are so many standards developed. Like we have International Electrotechnical Commission standards, IEEE standards, and European Union standards, and so many other standards for power quality problems. So these power quality problems will give you what is the tolerable level of different parameters. Okay, so let us see whether this power quality is only theory or whether there are any issues reported really in the physical system. So we will see some data where power quality problems are reported. So this is one survey, power quality disturbances in USA, which are reported from the customer side. So we can see the pie chart shows voltage sags and swells reported, around 24% of occurrences, and improper wiring, the problems due to improper wiring are around 27%, problem due to harmonics is 17% and so on. So customers have reported some of the power quality problems, and because of which there is a mal-operation of the equipment. And we also have a survey from the utility side. So we can see voltage sags and swells, around 55% of the cases are reported from the utility side. And loss of voltage greater than 5 seconds, it is around 13%, and voltage surges 6% and so on. So these are the power quality issues reported in a particular year, and year by year it basically changes. And this is the data in Netherlands. For example, we have voltage variations 2%, under voltage 25%, over voltage 2% and so on. So these are the issues reported in Netherlands. Okay. So in different countries we have data. And of course India, I also searched about data in India. I could not find out. If anybody has the data, you can just inform me. Let us see the financial impact of power quality. So we have 3 different informations I could find out. For example, in 2010 survey USA, the annual production loss due to power quality issues is around $150 billion. Okay, why we need this financial impact? Because we want to propose a solution. So after we propose a solution, we made a equipment and we want to install it. The person will ask, why should I install your equipment? Because that equipment is also too much costly, right? So then we have to say that if you don't install that equipment, the loss is more. Okay. So European Union, like according to a survey in 2003-4, the loss due to power quality issues is around 151.7 billion euros. And also we have one data in India, 2015 report is there. So the loss is around 20,000 crores per annum due to power quality issues, and out of which 57% is due to voltage sags and short interruptions, and around 35% is due to transients and surges, and remaining is due to other problems. So we also have financial impact reported in India according to a 2015 report. And we have different types of problems, and we have categorization of the loss also. So overall, if you see the total financial loss according to this table, it is around 149 billion euros, and according to the today's conversion rate, if you convert it, it is around 13,20,000 crores, okay, which is very significant amount. So if you can analyze the power quality problems and solve the power quality problems, you can basically decrease this financial loss. You may not get away completely, but you can slightly decrease the financial loss. So let us see how to analyze power quality problems. Basically what we saw is what is the problem of poor quality and what is its financial impact and impact on the industry. Now we have some motivation to analyze the power quality problem and try to find out some solutions. Now let us see two types of analysis. One is analysis of unbalance and analysis of harmonics. So using our basic circuit theory or basic mathematics, how do we analyze these problems? So let us consider analysis of unbalance. So here we see the time domain expressions for the balanced sinusoidal signals. Okay, the peak value is same and frequency is same, and they are phase shifted by 120 degrees. So this is the time domain representation. This is graphical representation. Now, if you consider unbalanced three-phase voltages, the peak value is different. The phase C voltage has higher peak value and phase B voltage has very minimal peak value, and they are also not phase shifted by 120 degrees. So there is 100 degrees phase angle and 90 degrees phase angle. So the phase angle is different and also the peak values are different. So this is a graphical representation of this time domain waveforms. Now we can also have phasor domain representation. If you draw balanced three-phase phasors, then all are having same magnitude and there is a phase angle shift of 120 degrees from each other. And this is the representation of unbalanced three-phase voltages. Okay, so you can see from the phasor diagram itself, they are not balanced. Now, how do we analyze these components? We analyze the unbalance using the symmetrical components. Okay, so we already know symmetrical components of phasor quantities in our power systems. Okay, so what we study is symmetrical components of phasor quantities. That is, if you have a set of unbalanced AC voltages, we can decompose into three different balanced sets: the positive sequence component, negative sequence, and zero sequence. And this is the expression for finding out the positive, negative, zero sequence component in phase E. We also have another equation for phase B and phase C, like VA0, VA1, VA2. We also have VB0, VB1, VB2, and so on. Okay, so here, as you know, A is a rotational operator. It is e power j 2 pi by 3, cos 2 pi by 3 plus j sin 2 pi by 3. So this theory is known to us. We apply symmetrical component to phasor quantities. Phasor means we are representing using a bold-faced font here, capital letter. Now, we also have something called instantaneous symmetrical components, so which is like used for the analysis of unbalance in the power quality solutions. So instantaneous symmetrical components means we basically consider the instantaneous voltages VA, VB, VC. So here small letter represents that these are instantaneous quantities, and we can find out instantaneous symmetrical components VA0, VA1, VA2 using the same matrix, same conversion ratio. But this constant 1 by root 3 here, it will be different. So it depends on what type of application or what type of theory you are using. But this is how we calculate the instantaneous symmetrical components also. So we will see some calculation for this. For example, if you consider balanced set of sinusoidal signals like VA, VB, VC are voltages and IA, IB, IC are currents. You can see there is a 30 degrees phase angle difference between voltage and current, but both voltage and current are balanced. Now, if you apply the formula here, the positive sequence component, instantaneous positive sequence component and negative sequence component are given by this expression, and substitute the time domain expression and simplify, we get VA1 equal to root 3 Vm by 2 sin omega t minus j cos omega t. And in case of current, we just have a 30 degrees phase shift, otherwise it is the same. Like the peak value is Im sin omega t minus 30 degrees minus j cos omega t minus 30 degrees. So you can see that instantaneous symmetrical quantity is a complex number. There is a real part and it has an imaginary part. And we can basically plot the vector, the real axis and imaginary axis we can consider. We can plot the loci of the tip of this vector as omega t varies from 0 to 2 pi. For example, if you consider omega t equal to 0 here, the real part is 0 and imaginary part is minus 1. Okay, so this dot shows the starting point when omega t equal to 0, and as omega t varies from 0 to 2 pi, this tip of the vector it traces a circle in anti-clockwise direction. Similarly, this is the loci of the tip of the vector IA1. So this starts here because omega t minus pi by 6 is there. So there is some phase angle difference between the two. And IA1 also rotates in anti-clockwise direction. So this is the path traced by the loci of tip of the vectors VA1 and IA. So these are the positive sequence components. You can also find out negative sequence components VA2 and IA2. So you will get the same plot, but it will rotate in anti-clockwise. It will rotate in clockwise direction. This is for balanced sinusoidal case. Now let us consider unbalanced sinusoidal signals. Okay, the peak value is different and phase angle is also not 120 degrees. So we calculated IA1 and IA2 positive sequence and negative sequence components, and we have plotted the loci of the tip of these vectors. You can see that IA1 and IA2, the path traced by the tip of the vector is an ellipse. It is not a circle. And also the IA1 tip is rotating in anti-clockwise direction, and IA2 tip of the vector rotates in clockwise direction. So if you have an unbalance, we can just notice it from this loci, from the graphical representation. Okay, always like from the equation, if you want to find out something, it is tough. So if you have some display where graphically it shows whether it is balanced or unbalanced, immediately when it becomes elliptical, you can understand that the signals have become unbalanced. So based on the instantaneous symmetrical components, we have also something called instantaneous real power, instantaneous reactive power, and instantaneous active current vector and instantaneous reactive current vector, and apparent power, and so on. So we have more definitions. Like, let us say if you have a voltage and current vector defined like this, these are all instantaneous values. Small v means instantaneous value, and the instantaneous real power is the dot product of these two vectors, and instantaneous reactive power is the cross product of these two vectors. Okay, this is a slightly new definition from your circuit theory. And we also have instantaneous active current vector and reactive current vector defined by these equations, and we can have instantaneous apparent power and instantaneous power factor. Okay, so these 6 are the new definitions: small p, IQ, apparent power, and the power factor. So this is how, this is a tool or theory used for analysis of the unbalanced waveform, based on which we can find out or control parameters for the power quality solutions. We will also see how to analyze the distorted waveforms. So if you have distortion in the waveforms, basically these are the distorted signals. We have a 5th harmonic component and 7th harmonic component. We also have a DC component here. 0.5 plus means the phase A voltage has DC. The peak values are not same. The phase A has a peak value of √2, and here you have 1.2 and here you have 0.85. That means there is both unbalance and distortion. And this is a graphical representation of these signals VA, VB, VC. Okay, so now we have to extract the fundamental positive sequence component of these unbalanced waveforms if you want to devise a solution for solving the power quality issue. Okay, so this is the algorithm for online extraction of fundamental positive sequence component. So what is the meaning of online extraction? Like, offline extraction means you just take the data, let us say for 1 hour, you just measure the samples, go to your laboratory and then put it in Excel and then do the program and all. But in case of power system, everything should be online. Online means the system is operating, and when the system is operating, you have to measure the sample, you have to do the processing in your microcontroller within some microseconds time, and within 1 cycle you have to give the solution, that is what is the reference or control signal for the inverter. So that is called online control, and for that we need online extraction, and that is possible only from the measured samples. So in this step 1 is to find out the instantaneous symmetrical components using this formula, and in step 2, from the instantaneous symmetrical components we will find out the instantaneous the phasor symmetrical components using this formula. So here basically what we want to get is, from this signal we want to extract root 2 sine omega t. So we want to filter out other harmonic components and DC component. We want to extract root 2 sine omega t from this. From this we want to extract 1.2 root 2 sine omega t minus 110 and so on. So in order to filter out these other harmonics, the T naught here, the integral time interval should be chosen as 10 milliseconds if the supply frequency is 50 Hz. Okay, for example 50 Hz means the fundamental cycle is 20 milliseconds, half of that is 10 milliseconds. We want to extract the fundamental component, so we choose T naught as 10 milliseconds, and because of that the 5th and 7th harmonic components will be automatically filtered. Okay, then we use inverse symmetrical components to find out the VABC vector, and then from VABC you can get the fundamental components. You can see if you go through these 4 steps, if you consider the waveforms here VA, VB, VC, apply these 4 steps, what we get is VA fundamental, VB fundamental and VC fundamental. Only the fundamental component will be there, and we can see the result of this algorithm. This is the original waveform which is unbalanced, and then this is the fundamental component. The dashed waveform is the fundamental component, and it is also positive sequence component. So this is how we do the online extraction of the fundamental positive sequence component from the distorted signals. Now the issue with this algorithm is it cannot be used for interharmonics. What are interharmonics? For example, here the harmonics are 5th harmonic and 7th harmonic. So we can also have some cases where the harmonic number is 5.5 omega t or 7.5 omega t or some 11.5 omega t. So this is not an integral multiple of your fundamental frequency. These are called interharmonics. If you have a term like 5.5 omega t, 7.5 omega t and so on, they are not integral multiples of the fundamental frequency, and they are called interharmonics. Now if you have such a term, if you choose T naught equal to 10 milliseconds, the harmonic component will not be filtered out. Okay, so what happens is we cannot have fundamental positive sequence here. So if you have interharmonics, this algorithm doesn't work. We have to go for some advanced algorithm. Okay, this is how we analyze the distortion. So now once we analyze this unbalance and harmonics, so let us see the solutions here. So some of the solutions for power quality problems like unbalance and harmonics. Okay, so the basic solutions are custom power devices. So custom power device means the technology of application of this power electronics to power distribution systems for the benefit of the customer. So that means if you solve any type of power quality problem using some power electronics technology, by applying that to power distribution system, then we can call it as a custom power device. And ultimately we need benefit to the one customer or a group of customers. If there is no benefit, there is no use of application of this device. So we have 2 major categories of these devices. One is network reconfiguring type, another is the compensating type. Okay, network reconfiguring type is solid state current limited, solid state circuit breaker, and then solid state transfer switch. So these are the 3 network reconfiguring type. And we also have compensating type, like there are 3 different devices which are well known. One is the distribution static compensator, and dynamic voltage restorer, and unified power quality condition. So these are the major devices which are used as compensating devices. So by using these devices, we can solve the problems of harmonics, that is called active filtering, and load balancing, power factor correction, voltage regulation, and harmonic mitigation. So all these problems can be solved by using these devices. Okay, so let us see what are the introduction to these solutions. Now the DSTAT distribution static compensator, it is used in the distribution system. Okay, so the STATCOM is used in the transmission system, the DSTATCOM is used in the distribution system. So DSTATCOM has more control flexibility and more functionality compared to a STATCOM. STATCOM generally is used for reactive power compensation, and in transmission systems generally we don't do this harmonic compensation and all. Okay, So in transmission system, the major problem is reactive power. So STATCOM generally caters to reactive power issues. In case of DSTATCOM, it is used in the distribution system, and we need to have more functionality here. It has to take care of voltage sags, voltage swells, or imbalance in the voltages, or it has to take care of unbalanced source currents and then harmonics in the source currents and so on. So DSTATCOM is having more complexity compared to the STATCOM. So generally DSTATCOM is a power electronics based device. It contains a current control voltage source inverter, and it is a shunt type of device. It injects current at the point of common coupling so that these three objectives are achieved. So the first objective is active filtering. So the load current harmonics will not appear on the source side. And the second objective is source current is in phase with the terminal voltage. That is, we have a unity power factor operation. There is no reactive power drawn from the source. And also the source currents are balanced even when the load is unbalanced. These are the major functions of the DSTATCOM. So we can see the schematic diagram of a DSTATCOM here. So this is only a single phase system. So we can basically extend it to the three phase system. Okay. So generally DSTATCOM is used in three phase system only for representative purpose. This is a drawn as single phase system. Now you can see this is called PCC, point of common coupling, where you have a common connection to the feeder, the load and the DSTATCOM. So this is the point of common coupling, and we inject a current ISH by the DSTATCOM, and DSTATCOM is supplied only by a capacitor. It doesn't have any active source. Okay, DSTATCOM doesn't require any active source like a battery or some other DC generator type of thing. We use only capacitor because DSTATCOM only supplies reactive power to the system. It doesn't supply active power. So we considered a feeder impedance also. So this is when you consider feeder impedance, we generally call it as non-stiff green. If the feeder impedance is neglected, we call it as a stiff green. Now DSTATCOM injects this current ISH so that these three objectives are satisfied. And how do we find out the reference currents for this DSTATCOM? So these are the equations using which you can find out the reference current for the DSTATCOM. The ISH is the current to be injected. In phase A, ISH A is given by the load current minus this term. Okay, so basically this algorithm is developed based on the instantaneous symmetrical components and so on. Okay, so this is not the only algorithm. I am just giving an example, but in the literature there are so many other algorithms for generating the reference currents for DSTATCOM. And this is only for the simplest case where the supply is balanced and also there are no distortions in the supply. Okay, this is the simplest case of reference current generation. Now for this, what you have to measure? We have to measure the supply voltages or the PCC voltages, VSA, VSB, VSC, and we also have to find out the average power drawn by the load. So PLAV here is the average power drawn by the load, which is same as the real power, but we have to find out that online. Okay, so what is beta here? Beta is the desired phase angle between the source voltage and source current. If you have a unity power factor operation, beta is related to the, I think it is around tan inverse by root 3, tan inverse 5 by root 3 something. So based on the desired phase angle between the source voltage and current, we have to choose beta, and this is the algorithm which will work for the balanced source, and there is no non-linearities in the load, and also there is no feeder impedance. So this is simplest algorithm. If you have more complicated cases, then algorithm has to be modified. Now we will go to the second solution, which is DVR. So basically DSTATCOM is a shunt compensating device which will act on the currents, and DVR is a series compensating device which will act on the voltages. It is connected in series between the PCC and the load, and it will inject a voltage VF in the system. So here also we only require a capacitor because DVR also doesn't supply any active power to the system. We only require a capacitor to the DVR. We don't need any DC voltage source. And since we are injecting voltage in series with the feeder voltage, the DVR can be used to mitigate the effects of voltage sags, voltage swings, and voltage imbalance. So all the problems related to the voltage voltage of the supply can be mitigated by using a DVR. Okay, so we also have a reference voltage generation for DVR. This is the one of the algorithms. There are so many other algorithms also. Here what we do is from the measured source current, we first compute the fundamental of the instantaneous positive sequence component. Okay, using this formula. Okay, measured source current is represented as a magnitude and a phase angle. From this, in the step 2, we calculate the phase angle of the load voltage vector. Okay, the phase angle of the load voltage vector is given by this formula, that is phi VLA1. So from this phi SA1F, we have to find out the phase angle of the load voltage vector. Then in the step 3, we have to find out the instantaneous symmetrical components of the desired load voltages. Okay, so if you have a star here, it is desired load voltage. The actual load voltage can be unbalanced, it can be distorted also, but the desired load voltage is generally a sinusoidal component. So we calculate the desired load voltage, and we have to use the phi VLA1 calculated in step 2 in step 3. Okay. Now in step 4, from this positive negative zero sequence components, from the symmetrical components, we find out the load voltages in the ABC domain. And these are all again instantaneous components. Now from that, once you know the load voltages references in the ABC domain, you can find out what is the voltage to be injected by the DVR. Okay, so VFA star is given by VLA star desired load voltage minus the present PCC voltage. Okay, so these are the 5 steps to find out the reference voltage for DVR, the dynamic voltage restorer. And again, this is one of the algorithms. So we have so many other algorithms for dynamic voltage restorer also based on the particular case. Now we have a third device called Unified Power Quality Conditioner, where we unify the objectives of both Disturbances and DVR. It has both shunt compensation and series compensation. So basically, if you have a PCC here, the voltage source here represents DVR operation, that is series compensation, and the current source here represents the Disturbances functionality, that is shunt compensation. Okay, and these two are coupled each other. For example, if you have a capacitor, for DVR also you have a capacitor here, and for Disturbances also you have a capacitor. So Disturbances is supplied by capacitor CDC, and DVR is also supplied by the capacitor CDC. In UPQC, there is only a single capacitor which is supplying both the shunt compensating device and series compensating device. Basically, these two are coupled through the DC link capacitor. We have two different configurations in UPQC. One is right shunt UPQC and left shunt UPQC. So here right shunt UPQC means the shunt device is connected to the right of the series device. So now you have both series and shunt compensations. That means it can solve both current related issues and voltage related issues. So if you have a current imbalance or distortion, it can solve. If you have a voltage imbalance, voltage sag or swell, then also this device can solve. Now this Disturbances, DVR and UPQC are traditional solutions. Now in the literature there are so many other advancements in these devices. For example, one of the advancements is a open UPQC. Okay, so if you consider a traditional UPQC, the location of both shunt and series compensating devices is the same. They connect at a particular bus. So we also have something called open UPQC, where the series compensating device is connected at the substation, and then we have some feeders and load buses. The shunt compensating device is connected far away from the substation. Generally, we will have one series compensating device and several shunt compensating devices for the individual customers. So this is called open UPQC because there is no physical connection between the series and shunt devices. Previously in UPQC, the series and shunt devices are coupled to a common DC-link capacitor, but here the series device is supplied to a battery, the shunt device is supplied to a battery. There are several shunt devices, one series device, and all of them are coupled to a communication link. We only have a communication link. The series device controller will say that you inject this much reactive power at this bus, and then it will inject that much reactive. So they are only coupled to a common communication link. So this is called Open UPQC. So this is one of the advancement in UPQC, and also we have another advancements in the renewable energy and distribution generation side. That is, nowadays we are having renewable energy sources everywhere. Okay, so in distributed generation and microgrid, we have solar PV or wind energy or some other distributed energy source. We are using some kind of power conditioning unit to connect this renewable energy source to the grid. Okay, so if you consider a traditional power conditioning unit, that is the power electronic interface used for PV or wind, the major functions are real power injection into the grid and MPPT operation of the renewable energy source. These two are the major functionalities of the traditional PC. Now the idea the people are working on capability to mitigate power quality issues using the same PC. So whatever functionality that we are talking about, like the power quality issues, can be mitigated by using the same voltage source inverter which is used to interface the renewable energy source. And also if you see a solar power source, so the solar PV doesn't give you power all the time. So you have, let us say, power, there is no power during night time. So when there is no power during night time, you can use it for compensating purposes. But what is the problem with this? If you are using it for additional functionality, we also have to increase the rating of the power converter accordingly. So if it is only injecting real power, we have to decide the current rating of the switches according to the real power injection. But if you have to inject the reactive power, we have to inject some harmonic currents. So for the increased current rating, you have to redesign the power converter. So with the same design, you cannot use it for power conditioning purpose also and power quality mitigation. You have to design your power converter again. Slightly the cost will increase, but if you see the overall cost of using a separate D-stat pump, maybe it is better to use the same voltage source inverter as a D-stat. So we have some small example here. So we have a wind energy system which is connected to the grid through a rectifier, boost converter and a multi-level converter. Here ANPC is active neutral point clamp inverter. So basically we are connecting this wind energy system to the grid using this power electronic interface. So traditionally we only inject active power to the grid. So now we have a only example where we are injecting reactive power. Of course you can change the algorithm so that it also injects some harmonic current if required. Okay. So in this case we have a small change in the control algorithm. We have a power factor setting, and according to the power factor setting we can calculate what is the reactive power to be injected into the grid, and accordingly we can calculate IQ reference. Okay, we are controlling this particular system using DQ domain control. So D axis current reference controls the active power component and Q axis current reference controls the reactive power component. So now based on the required power factor at the grid current, we can change the reactive power reference, and we can also inject reactive power. And if you want to change the harmonics also, we have to slightly change this control algorithm. Now we can see some simulation results here. So this is grid voltage and grid current, and this is the power factor, real power and reactive power. In the first case we are setting the power factor to 0.9 lead. That means we are injecting the reactive power into the grid. You can see that the real power injection is around 4 kilowatt, 8 kilowatt, and reactive power injection is 4 kVA. Now in the second case, the power factor is 0.9, but it is set to lagging power factor. That means we are drawing reactive power from the grid. So you can see the real power injected is positive and it is 8 kilowatt, and the reactive power injected is negative here, it is minus 4 kVA. Okay. So this is a small case study where the same power conditioning unit is used for the reactive power injection also, and by that you can solve some problems of the distribution system. And of course nowadays, like in the standards itself, like the power conditioning unit standards itself, it is mentioned that you have to give some reactive power support to the grid so that the short-term voltage interruptions or voltage sags are automatically mitigated. Okay, so to conclude my first part, so basically we have seen what is power quality. So power quality can be defined as supplying electricity to customers with minimum distortion and interruption. We have to have sinusoidal supply and we have to have continuous supply. Now, if you have poor power quality, it has significant impact on the performance and lifetime of the equipment. For example, because we have some 1 or 2 minutes interruption, we have to install UPS or some DC in all the buildings, right? That actually is adding cost, maintenance cost to the entire institution or organization. So that is one real life example of interruptions, short-term interruptions. And if you have a sustained problems in the voltage and current, there will be damage in the equipment. And if you have any power quality problems, you have to monitor the power quality problems and you have to characterize it using the characterization methods. Otherwise, there will be huge financial loss. And we can improve the power quality by installing custom power devices. And we have so many advancements in the custom power devices. We have seen different custom power devices, the traditional ones, and only there is some introduction to 2-3 new advancements like Open UTQC are using the existing power conditioning units as a power quality equipment for the reactive power injection. So this is what we discussed in the first part. In the second part, we are going to see the one of my papers where we have detailed study of the Dept implementation, and we will see the control of the inverter also on the reference current generation. So these are the some of the references used for preparing this presentation. And if you have any questions, you can ask me.
If you have any questions,
Sir, you have told that in online and offline mode of power quality monitoring and analysis, sir, in online, so what should be, if I design one power quality analysis algorithm and classification, what should be my device processing time so that I can get a real-time monitoring? Because if I design one real-time algorithm like signal processing and an artificial intelligence for classification, what should be my computation time of my device?
So
generally, in the real-time.
Generally what happens is if you purchase any customer device, any type of equipment, they give some tolerance and duration of the interruption. You have a voltage sag. Let us say the voltage decreases from 230 volts RMS to 200 volts RMS for some 2-3 cycles. Now the equipment will have a data sheet and they will give some tolerance range. For example, it can tolerate a under voltage of 10% for a duration of some 40 milliseconds. Okay, for that equipment, like it can tolerate only 40 milliseconds under voltage. Before that 40 milliseconds, you have to complete your algorithm and take the corrective action. If you don't take corrective action within that 40 milliseconds, then the equipment will damage. Okay, so you have to see the equipment data sheet and how much time is given according to the data sheet to clear the fault and to compensate the voltage side.
Suppose for power quality analyzer, it's a simple power quality analyzer. It uses the FFT algorithm and makes it shows in the. So if I design one robust online monitoring of power quality disturbances detection and classification, for that sense I need one signal processing tools like advanced DSP. I can use Guwahati and all these things, and for classification one AI technique. So what should be my the full processing time of my device so that it can detect the practical.
No, your overall processing time should be less than half cycle. Within some 10 milliseconds, you have to complete your algorithm.
So,
and as such, like if you see the basic algorithms, you don't need any very advanced computing architecture. Okay? So, for example, if you consider the simplest case here, what are the steps in this Dept company? Okay, so we have this online extraction. So you just have to complete this integral, and these are complex number or multiplication only, and you have to complete this integral. Integral is generally done in a controller by summation, right? So you have to have a memory, like store so many samples, and then there will be summation and there will be one product. Okay, so all this computation should be completed within half of second, right? That is 10 milliseconds. So that within 10 milliseconds you just start your corrective action. Okay, so your computation time should be as low as possible. And although this AI or other techniques they are discussed, their computational complexity is more. They require very high performance computing. You have to see whether it is applicable for our system or not. Okay, so let us say your equipment can withstand some 1 second or some 0.5 seconds of under voltage. There is no issue.
Okay, sir.
Anyone else?
Sir,
Yes.
sir, how we can monitor harmonics in transformer?
Harmonics in transformer. Like harmonics in transformer means you have to monitor from the terminal measurements only. We can measure voltage and current, right? That is the three-phase voltages and three-phase transformer currents. So from that you can get some data, right? If there are harmonics in the transformer, that is caused by the transformer input voltage and current.
Sir, is there any device or sensor which can directly measure harmonics?
Device or sensor, like we generally don't talk about devices, right? For example, you measure the voltages. So if you measure the voltages and you just plot it somewhere, you can see that there are harmonics.
Voltage sensor and current sensor?
You can just maximum you require a voltage sensor and current sensor. So now how do you know there are harmonics? You have to plot the data obtained by you. Okay, so you just store it in a microprocessor, or you store it in MATLAB also, MATLAB real-time environment. You just see it in the plot. Then you can see there are harmonics.
Algorithm is required.
No.
From data you can analyze whether there is a harmony.
Yes. Yeah, but exactly I do not know what is your application.
You are right, you are right. That is the only purpose.
Yeah.
These days because renewables are also injecting. So you want to check whether they are injecting through the transfer in the system or not. So before that they want to check whether there are some harmonics or not. Sag or some, any kind of harmonics. Power party disturbances. Directly they can check from the real waveform. They can compare.
Yes, they have to compare with the real wave.
Anyone else?
So,
first part is over, I think.
yes. So if you have any queries later also, any type of guidance, you can just send one email to me. So thank you.